Hello student, today I am going to explain to you regarding these properties of a continuous function defined in a closed interval. Here only if you check the syllabus, only the statements are needed, but we have to illustrate it, explain it through examples. So the first one will be this one. If f of x is continuous throughout the closed interval ab, and if fa and fb are of opposite signs, then in that case you can always find a number c lying between a and b such that f of x will become 0 at that point. That is, f of c will become 0. For example, in the case of polynomial function, if fx is a polynomial function, then we know that it is always continuous. So if you take it in a particular interval, say a to b, where the value of fa is greater than 0 or less than 0, but fb will be of opposite sign to that one, then in that case there will always exist a root lying between a and b, for which f of c will become 0, where this c should be a point lying between a and b. Now for example, I can take this one. Take f of x is equal to cos x. We know that cos x is a continuous function in the closed interval, say 0 to pi. Now what is f of 0? F of 0 gives you 1. And what is, because f of 0 is cos of 0 and cos of 0 is 1. And what is f of pi? F of pi is equal to cos of pi, and cos pi is equal to minus 1. Now see this one. F of 0 and f of pi are of opposite in sign. Then by this theorem or this property, there must exist a point C lying between 0 and pi such that f of that C should be 0. Now can you find a C lying between 0 and pi for which f of C is equal to 0? In this case it is quite easy. We know that pi by 2 is a number lying between 0 and pi, and we know that cos of pi by 2 is equal to 0. So you see that the statement of this one is true for this particular example. So now here you see that, so by the above theorem or by the above statement, there exists C is equal to, in this case it is pi by 2, such that f of pi by 2 is equal to cos of pi by 2 is equal to 0. So you see that if fx is continuous in the closed interval ab, and if fa and fb are of opposite in sign, then you can always find a number c lying between that interval. For example, in this case from 0 to pi, for which f of that c will be equal to 0, because c in this case is pi by 2. Now this theorem is called as the intermediate value theorem. So here we can name this one. This is the intermediate value theorem. The proof of this theorem is not needed, only the statement. It has already mentioned clearly in the syllabus. Now the next property of this continuous function defined in a closed interval ab is this one. If fx be continuous throughout the interval ab, and if fa is different from f of b, here I mean fa and fb need not be opposite in sign, but fa is different from fb. That means the value of f at a is different from the value of f at a point b. Then fx will assume every value between fa and fb at least once in the interval. So now in this case, if fx is continuous throughout the closed interval ab, and if fa is different from f of b, then fx will assume every value between fa and fb at least once in the interval. So to be more clear with this one, let us consider this example. Take fx. Fx is equal to, say, x square in the interval, say, minus 1 to 2. Now what is f of minus 1? It will be equal to minus 1 the whole square. It is equal to 1. And what is f of 2? This act as a, this act as b. What is f of 2? It is 2 square, because fx is x square. So f2 will be 2 square, and this will become 4. Now you see here that f of minus 1 is different from f of 2. They are not opposite in sign. Why? Because f minus 1 is also a positive number, and f of 2 is also a positive number. Now according to this property, this fx will assume every value between fa and fb. Now suppose C belong to this one interval, f of minus 1, f of 2. That is, C belong to, what is f of minus 1? It is 1. And what is f of 2? It is 4. Suppose C belong to this interval 1 to 4. And then I need to show that there will exist x belong to the interval minus 1 to 2, for which f of C will still belong to this one. So now here, then according to this property, then there exists C. There exists x such that f of x is equal to C, because C is the range or the value of lying between f of minus 1 and f of 2, that is between 1 and 4. So we need to show that there must exist x belong to this interval, say minus 1 to 2, such that f of x is equal to C. But what is f of x? By definition, I define it as x square. So implies that x square is equal to C. Now take the square root of this one. X can be plus or minus square root of C. So now here you see that we can find an x here, after taking the square root, x is called plus or minus C. But now, what is this C? Can it belong to this interval? So this implies that square root of C will be what? See, what is C? C belong to 1 to 4. So square root of C will belong to what? It will belong to 1 to, square root of 1 will be 1, square root of 4 will be 2. It will belong to 1 to 2. And we know that this interval 1 to 2 is still a number lying between, or a sub-interval of this one, minus 1 to 2. So you see that it is true in this case that for every fx, fx assumes every value between fa and fb. That means for C belong to the interval fa to fb, then you can always find an x which belong to this interval. In this case, what is that x? Which is equal to, it can be plus C. Here in this case, it will be positive. Why? Because C belong to only this one, to the positive interval from 1 to 4. So I can take here only the positive value of this x here, which still belong to this interval, because 1, 2 is a subinterval of minus 1, 2. And if you draw a number line here, this is minus 1, this is 1, this is 2. So 1, 2, it includes this one, that is, this C should lie between this one, in this interval 1 to 2, but minus 1, 2 is this one. But you see that when I include this one up to here, then you'll see that this part is also, this portion also is still a set which lies inside this whole interval minus 1 to 2. So for fa different from f of b, need not be opposite in sign, then in that case fx will always assumes every value between fa and fb at least once in the interval. Now next one will be this one, third property. A function which is continuous throughout the closed interval is bounded therein and attains its bounds at least once in the interval. That means a function which is continuous throughout the closed interval will also be bounded. That means you will always find the maximum value and the minimum value where fx lies, and it will attain that maximum and minimum value within that interval. For example, here if I take fx is equal to, say, cos x again in the interval 0 to pi. We know that this is a continuous function in this closed interval 0 to pi. Now, what is f of 0? It is 1. F of pi is minus 1. Now, what is the upper value? The upper or the greatest value? Upper value of fx in this interval, it is equal to 1. And what is the lowest value of fx? It will be minus 1, because the rest of the value will always lies between 0 and 0 to pi by using the between minus 1 to 1 by using or applying the second property. So now here you see that this is the maximum value and this is the minimum value. That means f of x will always lies between minus 1 and 1. That is, minus 1 will be less than or equal to cos x, less equal to 1. So whatever be the value of x lying between 0 and pi, excluding 0 and pi, then the values will always lies between minus 1 and 1. It cannot be less than minus 1 or it cannot be greater than 1. So it will always be between this interval minus 1 to 1. That is cos x in the interval 0 to pi will always lies between this minimum value minus 1 and greatest value 1. So here in this case, the maximum value, now what is the maximum value or the upper value of fx is 1, and it is attained within this interval only. It is attained at x is equal to 0. The maximum value of fx was obtained at x is equal to 0, this one, and the minimum value of fx was obtained at x is equal to pi, which are all the points lying in the interval 0 to pi. So a function which is continuous in the closed interval ab will always be bounded, and you will see that it will attain that its bounds means the upper value or the maximum value and the minimum value within that interval only. Now next, let us come to this one. Note, it may be observed from the preceding theorems, that means from this last two theorem of properties, that a function f continuous in the closed interval has the least and the greatest value m and capital M. Like in this, from this third property, that means it will have a maximum value or the least and the greatest value. That means in this case, I can denote this one minus 1 as small m and this as capital M. So the least and the greatest value m and m, that is the range set of f is bounded with m and m. That means f of x will always lies then between minus 1 and 1 in this particular case. Thus the range set of f is m, small m and capital M. That means the range set will be between that minus 1 and 1 for a function fx is called cos x in the closed interval 0 to pi, and that fx takes up every value between m and capital M. Then which means that the rest or the values lying and the rest of the value of fx will always lies between minus 1 and 1. That means between the lower bound and the upper bound. Now let us see this kind of remarks only. If the domain is not a closed interval, see, if the domain is not a closed interval, then the above theorem may not be true. That is, this theorem may not be true. A function which is continuous throughout a closed interval is bounded therein and attains its bound at least once in the interval. This is true only if the interval or the domain is a closed interval. But if the domain is not a closed interval, then in that case the above theorem will not be true. Then for that one, you let us consider this particular example. The function fx is equal to 1 by 1 plus mod x for real x. This is modulus of x. This is a continuous function and bounded and attains its bound. Now, what is the lower value or the attains its supremum for x is equal to 0. For example, if I take this one, x is equal to minus 1. What is f of x in this case? Okay, the function fx for real x is continuous and bounded, and it attains its supremum for x is equal to 0. Now, what do you mean by supremum? Mean the least upper bound. So now, what will be the maximum value that this one will? The maximum value of fx for x belong to a real number. Real number here, it is not a closed interval. So therefore, it will be this whole real line only in the number system, all points on the number system. So now here you see that this particular example will attain the maximum value when x is equal to 0. That is, we will get it as 1 by 1 plus 0. So it will be 1 by 1, it will be 1. So the maximum value of fx will be 1. The rest of the value will be to give you the minimum value. But it does not attain the infimum. That means, what is infimum? It is the greatest lower bound. So what will be the lower bound of this one? For x belong to R, then in this case it is bounded only. But it does not attain that minimum value. Not like for the case of supremum or the list of supremum or the least upper bound. In this case, it obtained the supremum or the least upper bound when x is equal to 0. But here we do not know for any x belong to R. For that one, we do not know exactly for which value of x it will attain that greatest lower bound. So in this case, you see that this result does not satisfy the previous theorem. Why? Because of the condition that fx, the domain of that function fx is not a closed interval. So you see that important of that closeness of the domain of the given function is that if it is a closed, then in that case it will always attain the supremum and the infimum within that interval. But in this case, it will not attain that one, because for x is equal to infinity, then in that case this will become 0. Now next, the function fx is equal to minus 1 by 1 plus mod x. This is continuous again. It is similar to this one. It is continuous and bounded, but attains its infimum only, but not the supremum. In this case, it will attain its infimum when x is equal to 0. Then it will become minus 1. That is the least value of fx. And then it will not attain the supremum in this case, because x here, the exact value of x in the interval R here does not exist in a particular interval where this fx will give you the maximum value for what if I take x to be in say minus infinity, then in that case it will be 0, but that infinity is not a point in the interval. So therefore this particular example will attain only the infimum but not the supremum. Now the function fx is equal to x for all x belong to the open interval 0 to 1 is continuous and bounded, but attains neither the infimum nor the supremum. Now see this one, fx is equal to x. This is bounded. What is f of a number? I mean, this 0 and 1 are excluded. Okay, but if you take, it is bounded by 0, because f of 0 will be 0, f of 1 will be 1. It is bounded by 0 below, and above it is bounded by 1. But this fx does not attain this value 0, because 0 is excluded from this one. So it does not attain the value 0 nor the value of 1. That is neither the infimum nor the supremum. Even though it is bounded between 0 and 1, but the value of f of 0 is equal to 0 is not cannot be attained by this fx is equal to x, because 0 is a point which is not included in the interval. So this is 0, this is 1, so this is excluded. So only the points which are greater than 0 and less than 1 will be inside this interval 0 to 1. Hope it is clear now. Now let me do one more application of that first property, that is the intermediate value theorem. If fx is continuous throughout the closed interval ab, and if fa and fb are of opposite in sign, then in that case there will exist at least one value, say x is equal to c, within the interval for which f of x is equal to 0, that is f of c is equal to 0, if they are of opposite in sign. Now let us see this particular problem which was asked in 2016. Show that the equation, this one is equal to 0, has a real root between 1 and 2. Also state the theorem that you use. Now what I need to do now is that we have to show that there exists a root lying between 1 and 2. So let us take this interval. Now f of x, you take, let fx is equal to x to the power 4 minus x cubed minus 3, this one. Now f of x is continuous in the closed interval 1 to 2. We know that every polynomial function is continuous. So therefore fx is equal to x power 4 minus x cubed minus 3 will be continuous in this interval. Now let us see what is f of 1. F of 1 will be 1 to the power 4 minus 1 cubed minus 3. So 1 will be cancelled, so it gives you minus 3. That is f of 1 is minus 3, which is negative. Let us find out what is f of 2. F of 2 gives you what? It will be 2 to the power 4 minus 2 to the power 3 minus 3. Now 2 to the power 4 will be 16 minus 8 minus 3. So minus 8 minus 3 will become minus 11. So 16 minus 11, which gives you 5. So this implies that f of 2 is equal to 5, which is greater than 0. So now you see this one, f of 2 is equal to 5 greater than 0. F of 1 is minus 3, which is less than 0. That means f of 1 and f of 2 are of opposite in sign. Therefore, by that intermediate value theorem, that is the first theorem, there must exist a point C lying between 1 and 2 for which f of C is equal to 0. So therefore, there exists at least one point C belong to this interval 1 to 2 such that f of C will become 0. That is C to the power 4 minus x cubed minus 3 is equal to 0. That is, there exists a root lying between 1 and 2. So that means the given equation fx is equal to x power 4 minus x cubed minus 3 will have a root lying between 1 and 2 by applying the intermediate value theorem. Here you have to state the theorem that you use. So you have to keep the statement of this theorem. The statement of the theorem that we are using in this case is this one, intermediate value theorem, and then you have to keep the statement of this theorem. That is, if fx is continuous throughout the interval ab and if fa and fb are of opposite in sign, then in that case there will exist a point C lying between a and b for which fx is equal to 0. That means there exists a root lying between a and b for which fx equal to 0, which means that c will become the root of that given function, or where fx vanish means the same thing only. So hope it is clear now regarding these properties of continuous function.